Okay, welcome to my home office. This is from some people I tutored. A mother and her son gave me this from Egypt. My name in Egyptian. A symbol, I'm not sure, in a cat. And my physics books, my logic books, my history of math books, and other stuff. So, systems of equations. We talked about why we need these things, done some. We solve systems by graphing, substitution, elimination. We'll go over substitution, which we've already done some. Do some more on this. So we need to know how to solve systems of equations. It's a building foundation for doing other more complex things with different equations. As we said, stuff in finance, economics, physics, chemistry. Like in economics, the break-even point. When you get like an income equation and a cost equation, you see where they meet, and it's your break-even point where the money you make is enough to just cover the expenses you have. You got these expenses for things. How am I going to cover them? By making money. When you are able to just cover your expenses, it's a break-even point. And this stuff comes up in a lot of other things, of course. But systems, one thing we do is solving by graphing. So we need to know how to graph equations. And then we graph two of them in the same coordinate system. And we see where they meet. And where they meet is the solution. So we can have, with systems of equations, lines can be parallel. Two lines, and so there's going to be no solution. That will happen sometimes if you graph them and they're parallel, and we can tell because they'll have the same slope. Or here, there's one solution. The point they meet is what we're looking for. What do the two have in common? What's the one point that's in both graphs, or the one ordered pair that's in both equations? What's the similarity they have? Or you got two different equations, something equals something, something equals something, but when you graph them, they're the same thing. Then there's infinitely many solutions. Okay, any point on the line will work. We can't just say infinitely many solutions or whatever we want. We want to say any point on the line, to be specific. So these are our possibilities. We can have no solution, have one solution, infinitely many solutions. So when we're going by graphing, if we got something like y equals 2/3 x plus 4, y equals 2/3 x minus 1. The slope is the same, but the y-intercept is different. So if we graph these, we're going to have one kind of sort of like that, and the other kind of sort of like that. And they're going to be parallel. They're going in the same direction, so no solution. Okay. When you have y equals, that's only when you can tell. You can't tell any other time. Y equals whatever, then, and only then, when it's set up like this, y equals mx plus b. Then we can get the slope, and if the slopes are the same, the lines are parallel, they're never going to intersect, no solution. If we got, of course you can stop the video and rewatch or stop, take notes and stuff like that. So if we have y equals, let's say the way what comes up a lot, like 3x plus 4y equals 10, 6x plus 8y equals 20. If we notice that all these numbers are 2 times these, then it's just a different form of the same line. Because we could divide out by 2. If I divided by 2, everything, that and that and that, divided each thing by 2, then notice we get 3x plus 4y equals 10, which is the same as that. So they're really the same equation. They do the same graph. So here we'd say any point for our solution, any point on 3x plus 4y equals 10. Cut. So any point on here is a solution to the system because the equations are just different ways to name the same thing. Just like we do with the positives like we talked about. Bob, the mayor, is running in the park. Bob and the mayor name the same person in a different way. Or like we can have a nickname. Or sometimes someone can call you by their last name, first name, in a context last name, same person. So different names for the same thing. Okay? Now, so we looked at no solution. Now, then we had infinitely many solutions when they're like that. Then we can have one solution, which we've seen some of. So if we have y equals 2/3 x plus 4y equals negative 1/2 x minus 1. When the slopes and y-intercepts are different, then we're going to have a solution. We can graph it and figure it out or solve it in some other way. It's just an illustration. So and I don't know if this one, I just made it up off the top of my head, so I don't know if it would work out nicely if we graphed it and stuff. So I'm not going to work this one out right now. We can do a different one that would work out. Or, so as long as the slopes are different and the y-intercepts are different, you'll have a solution. Or, if you got as long as at least one of these is different, then you're going to have one solution. This doesn't matter as much. It's just these four numbers control the slope, and if the x's are different or the y's are different, then you'll have a solution. Okay, let me graph it and see. So you'll have one place. So for those, if you graphed them, they'd meet at one point, and that's your solution. So, for example, we've already done some, but if you got like y is 1/2 x plus 1, and y equals, let me see, I do if I do these and I graph them, the slopes are different, so there'll be one solution. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And so this one, x plus 2, y-intercept is 2. Use a different color. Slope is 1. 1 over 1. So up 1 over 1. Up 1 over 1. Down 1 over 1. And again, if you are a little rusty on this from years past, review this stuff in the book, on YouTube videos, and worksheets you can find with answers. Get your graphing down. We've gone over this in class, and something that should have been up in the past. Maybe it was, maybe it wasn't. For most of you it was. So review it so you know how to do it for this. Then 1/2 x plus 1. Y-intercept is 1. Slope is 1/2. Up 1 over 2. Up 1 over 2. And then if we're 1, down 1 over 2, down 1 over 2, do a different color. Then connect the dots. Notice they hit right here. So we have one, up one, rise, run, so -2. So cool. So our solution's -2, 0. Notice it works in both equations. It's one thing to check. Computer, what the heck? You went to sleep. Is this still going? Let's see. Oh, good, still recording. Okay, that was weird. I need to like watch that. So, we got, if we put in a -2, so for this one, 0 is 1/2 -2 plus 1. Half of -2 is -1. -1 plus 1 is 0. So it checks out. That's right. Then we want to see if it works in the other one. 0 is -2 plus 2. So of course we get the -2, put it in place of the x. 0, put it in place of the y. Because ordered pairs are x, y. X is -2, y is 0. -2 plus 2 is 0. So it's correct. Then of course in this one, same thing. -2 in for x, 0 in for y. See if it's the same. So here we're checking. Does it work? Did we do it correct or did we make a mistake? So there's solving by graphing. Again, which we've already done. We did solving by graphing. Then we spent some time reviewing graphing in class, doing some graphing. Then we're getting back to this. It's in the book, something to review. So there's solving by graphing. And now I'll do some substitution and elimination in different videos. Cool. Turn this thing off.